Not where in the world did it put my chart? It's all ready to write. Okay, well, once the camera screw up. No, that's good. Okay, now. Okay. Find linear equation. There's two problems, okay? A line through these points, a line with this slope through this point, right? Just a point slope or 2 point. Okay, so, okay, first of all, first problem. Point backward apostrophe A, backward apostrophe C. In my case would be 5, 9. So. Put 5 here. We'll put 10 up here, so 9's about here. I just need a representative graph. It doesn't have to be perfect. Although if you want to take the time to use straight edges and so forth. Okay, but if you got a bunch of them to do, you're not going to really have time to do it with all of them. But for the first several you do, that's the way your mind wants to work. You don't have to just slop it down the way I do. But also develop the skill to slop one down if necessary. Yeah, and I don't like that, but I'm not going to forbid it. Graph paper is great if you need precision, but if you don't have graph paper, you're helpless. Okay, can you slop one down to the back of an envelope? You happen to have an inspiration driving down the road and you want to track yourself and get in the graph. Okay, you got to be able to slop down that graph quick, maybe avoid the record. If you're using drafting instruments, man, you're in trouble. Well, that's neither here nor there. Okay, you should be able to draw a representative graph without making it totally precise. Sometimes you want a totally precise graph, and graph paper is a great way to go. Okay, we're just scoping out the problem. You're not going to see me do that. You're not going to see me provide you with graph paper for the test either. Okay. I want you to think about scaling and all that stuff. Graph paper. It's handy, but it kind of constrains you too. Okay, well, anyway, you got D, B. Let's see, in my case, D would be, well, B is 7. So we come out to the point 12, 7, which if this is 9, would be about that. Okay, maybe we'll put it along. There's about 7. There's about 7. So I'm just gonna say that's 12, 7. We don't need squares on the paper to see what the labeling is. And then I sketch a line through the points. And then I go ahead and do my fundamental triangle. And I see that the rise is -2. And the run is, well, there's 12. 7. And the slope is, and the rise over run, which is -2 seconds. You can use a formula for that. Formula is a good formula, but understand that's all you're doing. If you're doing y2 minus y1, that's 7 minus 9, that gives you -2. If you're doing x2 minus x1, that's 12 minus 5, which gives you 7. And I wrote that out. I could even write run equals x2 minus x1, etc. Okay. Make it graph big enough to write all that out if you like it, because that reinforces everything. Okay, so we know what the slope is, we know what the graph looks like, we can even estimate that the b-intercept or the y-intercept will be around 10. If you trust my hand sketch graph, which I don't, okay? But it's actually probably going to be fairly close. You could even make a triangle here. You know this side, you know the slope, you could find this side, so you could find b without even plugging in to the equation, okay? But that's not the method. I'm just going to do that by one method. I'm not going to go to that. In pre-calculus class, I would expect people to be able to do it that way too. Okay, so we've got y equals mx plus b. So y is negative 2/7 x plus b. And multiply both sides by 7. Now that step would really be 7 times the quantity, negative 2/7 plus b. I didn't write it out that way. But then you do 7 times that quantity, the distributed velocity is 7 times this plus 7 times this. Okay, so you get 7y equals negative 2 plus 7b. At negative 2x. Put my x on here. Okay. Now I've got an x and a y, I can pick either point. So what I'm going to do is I'm going to say, okay. Picking the point 5, 9. Get this. Now, let's see. So this comes from the fact that the 0.59 is on the graph. We explained that, y equals 9 when x equals 5. So we plug in 9 for y, 5 for x. And it gives us 63 equals negative 10 plus 7b. We add 10 to both sides. And we get plain old 7b over here, but I'm going to write this over here because we just kind of like to see a variable on the left. It's not necessary. 7b equals 73. So b is 73 over 7. And if we want to locate that on the graph, it'd be 10. 37. So pretty close to 10, a little more, a little higher than I had it. But don't fall. Okay. Now, if you did all this and got a value of b equals 3. Okay. Well, you know b ain't no b. Okay. The y-intercept is here. Okay. Y-intercept is up there. So we can kind of then reinforce. One check is there's your y-intercept. This is plausible. The other check is plug in 12 for x and see if you get 7 for y. X is 12 is y equal to 7. Well, our equation is we got b, we've already got the slope. And I'm not going to write 10 and 3/7 here. I'm going to write 73/7. Because when we do the arithmetic with our fractions, we don't have to convert a mixed number to the proper fraction. Okay, got to be able to deal with the fraction. So we check this out. Okay. Well, if okay, well, let's check it. Plug in y. You know, it's hardly conceivable. I could have made a mistake or somewhere. Let's see what could be, it's all pretty simple. This doesn't look like it's gonna check. You're gonna get like 71/7. Well, that's because I plugged in 7 for X instead of plugging in 7, instead of plugging in 12. I wasn't very careful there. Should have been 7, there should have been 12. Okay. Now we get Y equals minus 24/7 plus 73/7, which is 49/7, which equals 7. Y equals 7. So we plug X equals 12 in here, we go through the equation, we do the arithmetic, and we get Y equals 7. Okay. Let's be sure to plug X in, so plug in Y in. Okay. This line. Okay. Slope 1/5. 30.74. I can sketch that. This is 7 and this is 4. Here's a 0.74. Slope of 1/5 means if we move over 1, sorry, if we move over 5, we move up 1. If the run is 5, the rise has to be 1. So, unsurprisingly, my label 7/4 is kind of in my way, so I'm going to get rid of it. I'll label it here. And we should understand that the slope of 1/5 I could use a run of 5 and a rise of 1. Or I could use a run of 10 and a rise of 2. Any rise and run that gives me 1/5. If I want to sketch a graph, I can do that. Now that rise is a little bit high. If this is 5 and 1's about, about 2.0. Okay, so if I sketch a line through these points, then I would estimate a y-intercept of about 2. Now, this run and this rise weren't constructed all that carefully. And the 7/4 is, that's 4, yeah, that's maybe not too bad. Okay, so this is just a ballpark to give me a picture. It's a fairly reasonable ballpark, but if I find that the y-intercept is 3 or 1, I'm not going to be too surprised. Okay, looks like about 2. That's my sketch. Okay, so now what do we do? Well, we say, okay, y equals mx plus u. M at 0.74 leads us to the conclusion that 4 equals 1/5 times 7 plus b. In other words, seven, 4, and the 1/5 give us this. In other words, I plug in 4 for y, 7 for x, 1/5 for the slope, and here I have it. Now I just got to solve for b. I multiply both sides by 5. Forget this, which is on 20 equals 7 plus 5b. Five b equals 20 minus 7 equals 13. B equals then 13 over 5. Okay. So now the equation. Y equals 1/5 x plus 13/5. So that 13/5 is like 2 3/5. Okay. Actually, it's closer to 3 than 2. I thought it might be a little bit lower than that. It's more like area B and Y intercept. But we can look here. We can say that okay, maybe this is zero two is plausible. Y-intercept is really 0. 2 3/5. Okay, should be a little higher. Okay, well, let's check the algorithm. We can see that the slope is 1/5. The only point that we have is 7/4. Really, we're just checking our algebra here. If x equals 7, does y equal 4? Well, we plug in 4 equals 1/5 of 7 plus 13/5. Of course, that would mean 4 then equals 7/5 plus 13/5. So is 4 equal to 7 plus 13 over 5? Well, that would be 20 over 5, and 20 divided by 5 is 4. 4 equals 4 and it checks. Okay, so either way, you need to be able to check your work. That's where you get feedback on whether you're doing it right or not. Not just open math says, that's wrong. Okay. Do your own check and you figure out where you went wrong, or you get a good lead on figuring out where you might have gone wrong. Okay. Okay. So the high temperature two days ago, that would have been Sunday. I just want to say, high 2 days ago is 38 Fahrenheit. High today forecast to be 60. If that works out, then what are the rate? Oh. I don't know where the word was coming to. The rate Which the high temperature is changing. And of course, this is an average rate. The change between yesterday and today is different than the change from day before yesterday to yesterday. So rate is not going to be changing at a constant rate. The temperature is not going to be changing at a constant rate. So what's the rate? How are you going to approach this problem? Okay, it's really a good idea to sketch a graph, and that's what somebody suggested. Okay, so I'm glad you suggested it because it's kind of the way you pretty much most of you don't want to do it this way. Depends on how your brain's wired. Okay, but what's changing with respect to what? Okay, well, you know, your book says the average rate at which temperature is changing. Yeah, every text. I like to say, with respect to what? And it's changing with respect to time. There are two quantities here. I've given you information on temperature, I've given you two temperatures, right? And I've given you two times, but I haven't put them on a scale. So this is time. I'm just going to say time in days. Okay. This is temperature. In Fahrenheit degree. So how would you put 2 points on that graph? Okay, now, two ways we can do this. The temperature changed by 22 degrees Fahrenheit, right? It went up 22 degrees Fahrenheit in 2 days. That's an average of 11 degrees per day. So it's a straightforward calculation. You just understand what rate of change means, okay? So you can do that. You can say change in temperature over change in time. I recommend focusing a little better that you put these things on a graph, okay? So let's say I've got 4 days here. I'm only going to need 2 days, but I'm going to put 4 days on my graph. In temperature, well, I'm going to put 80 up here because 2 to the third is 8. Means I can divide this in half at least 3 times. So 80 divided in half, I get 40. Divide that in half, I get 20. By this interval in half, there's 60. And that's enough. So now I can put 2 points on my graph. Now, most of you put 60 degrees at day 2. Okay. And that's perfectly all right. Then you put 38 degrees at day 0, because that's 2 days earlier. One of you chose to put 60 degrees at day 0, and then 2 days earlier was -2. Okay. You get the right answer either way. So I'm going to do it even a different way. I'm going to put, let's see. I'm going to say Sunday was day 2. Okay. Actually, I'll extend my t-axis just a little bit. And put 5 there. So I'm going to say that was Sunday. Okay. Now, if you're given this thing and you don't know that today is Tuesday, so 2 days ago was Sunday, you can pick any day. Okay, let's assume today's Friday. Then Wednesday, okay, you can make it real specific. There's nothing in the problem that forbids that, and nothing in the solution that depends on what day the day is. Okay, until I told the world out there that today's Tuesday, they wouldn't have known. And I kind of checked the date on the video and say, well, it was February 14th. But that was 3 years ago. Let's see, what day of the week was that? I don't care what day it was, it was Friday. Okay. Now, the reason I say all that is I'm going to say, okay. Day 3. Let's say that was Sunday. So today is day 5. Just to flesh out the details, make it easier to think about. Now, you don't really, this is when you calculate your head. 22 degrees in 2 days is 11 degrees per day in the average. Okay. And once you get used to doing rate of change calculations, it's probably the way you're going to think about it. Some of them are a little harder to visualize. So I recommend that you make a graph for everyone. And it also gives you a better understanding of what a graph you're telling. Probably not necessary much of it, probably, but it's a good idea. Okay, so Sunday, it was 38 degrees. So here's 38. And today it's 60 degrees, so. Okay, so this is the point. 560. This is the point. 338. Now I sketch a straight line through these points. Keep it lined up. I can still leave my 338 there. I had to put it somewhere. All right. And then I complete a fundamental triangle. Now, if I do the triangle from here to here and up, that 560 is going to get in the way of labeling my rise. I'm going to put the triangle up here. We're going to get the same result. And to keep it straight, we put arrows in these so we know whether our rise is positive or negative. Don't forget, make it positive if it's up, negative if it's down. So the rise is -60 minus 38, which is 22. Now you can say that's y2 minus y1, 60 minus 38. Okay. But you don't really need the formula to do that. Still, kind of remind yourself, okay, there's my y2 minus y1. Do it without thinking y2 minus y1, then see that it's y2 minus y1. Or do it with y2 minus y1, then say, well, I really didn't have to put labels in those. I know it's 60 minus 38. And I'm going from 38 up to 60. All right. Then from here to here, we'll go from 3 to 5. Okay. And then the slope. Is rise over run, which is 11 over, sorry, it's 22 over 2, which is 11. So I put 11 here. Put a little box around it. There's my whole calculation slope. Then I relate this to the definition of rate of change. I don't just say, well, the slope is rate of change. I mean, it is, you can get away with that, but you learn more and have a better command of it if you then come over here and say, okay, so what's the rise mean? What's the run mean? You're interpreting the graph. Okay. It's 22 degrees Fahrenheit, right? And it's plus 22. The temperature went up by 22 degrees Fahrenheit. The rate of the change in time, and that's plus 2 days. So the slope is .22 degrees Fahrenheit over 2 days. Well, you divide 22 by 2, you get 11. You divide Fahrenheit by days, and you get Fahrenheit over days, right? And that's Fahrenheit per day, degrees Fahrenheit per day. Then you remind yourself that the rate is the change in temperature over the change in time. Change in temperature is your rise, change in time is your run. Here's your rise. Here's your run. That equals, again, 11 degrees Fahrenheit per day. And you connect everything with the definition of a rate of change. And everything comes full circle, and you've got a nice little package of understanding there. You have a better understanding of what the graph would tell you. You have a better understanding of rate of change. Now, the other thing is, you're going to get exactly the same rise and run if you call it day 1 to day 3 with the same temperatures, or day -2 to day 0. Okay, and that makes perfect sense. Thinking in terms of today, 2 days ago would be -2. Wouldn't make any difference. Now, if you do the equation, well, then you have something. Now, what would the equation tell you? Well, the equation could be used to answer the question, okay, at the same rate, how long is it going to take us to get to 120 degrees? Ridiculous question, because we know it's not going to be 120 degrees. It's this latitude in mid-February. Okay, the record high somewhere in the 70s. Record lows, little lows. Okay. So I could get my y equals mx plus b function very easily. Once I get that, I just let y equal 120 and solve for my t, or my x, whichever you want to call it. Okay. So that's a little further than we want to go when we're just talking about applications of the slope. This isn't a linear equation, it's a quadratic equation. You've got h squared there. A couple other conditions on a quadratic equation. Form of this equation, ax squared plus bx plus c equals 0. With a, now it's actually, instead of an x, it's an h. Doesn't matter what this variable is. There's your standard form of a quadratic equation. The number in front of the square is a, because a goes in front of x squared, right? And 2 goes in front of h squared. So number in front of the squared term is 2. B is a number in front of the unsquared term, the x term. Here it's h, but for the first power. Okay, b is 10. And c is the number left over. The solution is x equals negative b plus or minus the square root of b squared minus 4ac over 2a. And I guess I should write up here that instead of x, we've got h. So I can say in this case, it's h that's equal to this. Well, you just plug these three numbers in here and simplify it, and you get two solutions. So that's all I'm going to say about it right now, but it'd be worth doing that. You got those numbers. Okay.
One place.